Hello, pre-calcers. So, it's the first Friday night of my winter break, and I thought, what a better way to spend my Friday night than recording some trig lessons for you. Alright, so if you have your notes packet, take out worksheet, it's 7. We're also gonna probably look at 8 next if you're on a roll here. There's I don't know if it's blue still, but there's a reference sheet that you're gonna want to have handy as well. So we've talked about the right triangle, trig functions, and the applications to them, basically just in reference to any old right triangle. But we're going to start talking more now about the unit. We're going to start developing the unit circle. And we're going to come up with some other formulas for sine, cosine, tangent, cosecant, secant, and cotangent. And those have more to do with thinking of the angles on a coordinate plane. So trigonometric functions of any angle, instead of using opposite hypotenuse and adjacent legs of triangles, we're going to relate them to coordinates basically. So we have the point x and y, and then if you draw a point xy, which like they have a diagram here where it's a terminal ray over here in the third quadrant for their example, you can create a right triangle, and then they're going to call the hypotenuse r. So instead of using the old terminology, they're going to have this new terminology that's frankly just a lot easier. It's more simplistic, believe it or not. Generally in math, the more you learn, the more simple the formulas become, because we're just tired. We want easy formulas. So x and y and r, you're going to be able to correlate with the coordinate plane, but also with the trig knowledge that you have. And these are the formulas that you need to know. Where it says x can't be 0, y can't be 0, and so on and so on, that's because the function would be undefined if that happened, because you would have a 0 in the denominator. And then the value for r is just solving for the hypotenuse of a Pythagorean theorem problem. So that's r. So yes, you must memorize these. And probably, if you took a trig course, you already kind of have them memorized. Let's see, this is the same set of formulas, same diagram. Let's move on. Oh, we have to always think about theta as being the reference angle. So remember, the reference angle is the acute angle that would measure to the nearest x-axis part. So it's going to be acute. And if you're working with what we call a quadrantial angle, we don't have a reference angle for those. So we'll talk about how those are special later. Mrs. Hofbauer uses a cute little bow tie reference. So basically, if you have an angle here, whoops, it's supposed to be straight, here, the bow tie part she's referring to these are your reference angles. A lovely drawing as always, Abruzzo. Congratulations. Alright, so we need to find the reference angle and then find the trigonometric functions. Make sure you understand what functions are positive and what coordinate, what part of the coordinate plane. So this is another thing that we're going to need to remember. The mnemonic device that I like to use is all students take calculus, but that stands for all and then S stands for the sine function, T is tangent, and C is cosine. And those refer to which trig functions are positive in that quadrant. Now when I say sine, I'm also referring to cosecant, because sine and cosecant are just reciprocals of each other. But if we just use the big 3 formulas, these are the ones that are positive in each quadrant. So all of them, just sine, just tangent, cosine. For me, because I'm like a really visual learner, I always graph it out, and then I don't have to think super hard about whether it's positive or negative, because even though they're, triangles, if I think about the ordered pair right here, this is a positive A value, but the B value would be negative because it's traveling down in the coordinate plane. So even though it's not really proper to call the leg of a triangle negative something, I'm still gonna. Alright, so finding reference angles, these are the rules that you probably had back in your algebra life. For me, it's just easier to draw it. I don't really care for more formulas in my life. These are the quadrantial angles. So 0 degrees, or 0 radians, and then up here at pi over 2 radians, it's 90 degrees. So whatever time you're on the axes, you have a quadrantial angle. And we're not going to talk about what's the reference angle of a quadrantial angle, because it doesn't really make a lot of sense to do. They're their own special little things. So the first task we have for ourselves is to sketch the angle and then find the reference angles. This is one of those cases where, like, it doesn't make sense to memorize that weird chart earlier. So 330 degrees would be, like, remember it's 180, 270, this is 360, so like a little bit under here. So here's 330, and you should draw like a directional arrow going this way. But the reference angle, alpha, is the distance from that terminal side to the nearest x-axis. So that would be a 30-degree reference angle. So here for negative 3 pi over 4, since it wants me to travel negative, we do have to think about that. This is 0 pi, this is negative pi over 2, and this is negative pi. So if I think about where negative 3/4 pi would travel, or where it would be, that would be right here. It's supposed to be in the middle. I did not do a good job. But it traveled this direction, negative 3/4 pi's. And if you're trying to figure out how far away it is to the nearest x-axis, it is 1/4 pi. Reference angles, remember, are always positive because it's measuring distance, technically. Alright, let's see here. And they want you to call them alpha. 9 pi over 6. Okay, so I love fractions. Now, if it bothers you, you can, oh, you know what? We gotta reduce that. Hello. It's 3 pi over 2. I don't have to do any work. So 3 pi over 2 is right here. That's what the angle looks like. And then when it says find the reference angle, since it's quadrantial, there is no reference angle. So that was a lot easier than I thought it would be. 11 pi over 6. Okay. I think I'll do this one and then we'll stop doing reference angles. So 11 pi over 6, if I start thinking about where my fractions are, that's really close to 12 pi over 6, and wouldn't 12 pi over 6 be 2 pi? So he's just under 12 pi's over 6, so he's like right here. So if I think about how far away, remember this is 12 pi over 6. 12 pi over 6 and 11 pi over 6 are 1 pi over 6 away. Now, what I was saying earlier before I got sidetracked from the talk of quadrantials, if the radians and the fractions is just boggles your mind and you just have a really tough time thinking about it, you can always convert to degrees, but then you got to convert back to radians when you're done. So is it worth it? I don't know. Sometimes you just got to muscle through the fraction. Alright, moving along. Again, this is that review concept. This problem is already done on your notes, so I'm not going to go through it, but basically they gave you the ordered pair. Negative 9, 12 is on the terminal side of some angle that was drawn. And if you think about this as being a triangle made with the reference angle, which is this guy right here, they labeled this leg as negative 9, this leg as 12, and then doing a little Pythagorean theorem, they found out that the r, or the hypotenuse, is 15. So they still set up the same sine, cosine, tangent, and all the reciprocal functions, angles, ratios, but using those formulas is just a lot faster. So, 2, negative 5 would be like here. Lovely drawing as always. And doing a quick calculation for r, that would be 2 squared is 4, negative 5 squared is 25, so r is the square root of 29. So for me, if I'm finding the 6 trig functions, I know that cosine and secant should be positive, and those should be the only positive functions in this quadrant. However, I'm not going to think too hard about it, because I already have my signs written down. Cosecant, secant. If you are the kind of kid who often messes up on signage, if you want, you can put negative signs in front of the 4 trig functions that are negative here. Alright, so sine is y over r. So remember, this is x, this is y, and this is r. So y over r would be negative 5 over square root of 29. And then if we rationalize that fraction, hit numerator and denominator by square root of 29. Negative 5 square root of 29 over 29. So cosecant would be the reciprocal of, I would do the reciprocal of that version. negative square root of 29 over 5. Cosine is x over r, so that would be 2 over the square root of 29. So again, we're going to have to rationalize that and get 2 square roots of 29 over 29. Secant is going to be the reciprocal of this original setup, so square root of 29 over 2. And then tangent is y over r, so y over x. Hello. And then go ahead and reversing that, x over y. Well, we already took care of the signs, remember, so that was smart of us, wasn't it? So there are your 6 trig functions. Not really that exciting, is it? This next one is going to be a little more exciting simply because I can tell from the nature of the coordinates that you're going to have some reduction when you go to simplify the 6 trig functions, but you know, as I look through my examples here, I think we have more exciting stuff to do, so I'm just going to skip that one. Alright, so here's some extra practice, right? Find the exact value of the trig function of quadrantial angles. So we are not able to do the reference angle business because they're quadrantial, so I think about what's going on here, and 270 is down here. So we are somewhere along this ray. Now in a moment we're going to have, a day, we're going to have the unit circle developed, and you're going to get some more understanding about what this all means. But for now, you just have to pick some ordered pair that exists down here on this ray. So like for instance, this ordered pair right here could be something like 0, negative 1, yeah? So if that's my x and that's my y, my r would be square root of 0 plus 1, which is 1. So when I go to set up the cosine, knowing the formula is x over r, the x value is 0, the r in this particular example came out to be a 1, 0 divided by anything is still going to be a 0. So no matter what ordered pair I chose along that ray, it would have come out to a ratio of 0 over something, and therefore the cosine of anything for 270, along 270, would be 0. So cosecant of pi over 2, if I think about where pi over 2 is, that's up here. Oh, okay, that was supposed to be a vertical line. So that's the ordered pair 0. Let's go 0, 1, you know, be crazy. Here's my x, here's my y, and then the r would come out to 0 plus 1, so square root of 1 is 1. And then cosecant, remember, is reciprocal of sine, so it's r over y. So r over y would be 1. And then cotangent of negative 90, that's a good one. Alright, so negative 90 would be going negative this direction, so right here. So something down here on this ray, let's call this ordered pair 0, negative 1. I don't have to find r because cotangent's formula is x over y. So x over y is 0. Now none of those 3 examples came out to something divided by 0, but like for instance, if they wanted tangent of negative 90, we would have saw that to be negative 1 over 0, and that's undefined. So those are possibilities on those quadrantials. These special right triangles are going to be really important when we talk about the unit circle and developing the unit circle. One of our major tasks coming up is to develop the unit circle. So, alright, here we go. 30, 60, 90s and 45, 45, 90s. So, if I back up one screen, those were the generic formulas from geometry. On a 45, 45, 90, the 2 legs it's isosceles triangle, so they're the same size. And then usually, you guys called this x times the square root of 2. And then, if you remember from geometry, sometimes these didn't come out so pretty, so you had to do a little work. On a 30, 60, 90, the small leg, the one that's across from the 30-degree angle, is an x. The hypotenuse is double whatever that x is. And then the medium leg, the one that's across from the 60, is whatever x is times an additional square root of 3. So a little funky pattern. It was just basically a shortcut to doing Pythagorean theorem on very special triangles. So here, 5 pi over 3, I already drew it for you in the 4th quadrant. If I think about his reference angle, because that's the angle that I'm interested in here, this is 2 pi, so that's 6 pi over 3, and this is 5 pi over 3. So in between here must be pi over 3. And if I think about converting pi over 3 to a hello, degree measure that is 60 degrees. Now, in hindsight, it probably would have been faster if I just converted 5 pi over 3 to degrees right away. And I would have got 60 to 300 degrees. And then I would have said, oh yeah, clearly, like, that's a 60-degree angle right there, because this is 360. Alright, so anywho, I have a 30, 60, 90 triangle. That's the moral of my story here, guys. So this is a 30-degree angle, that's a 60-degree angle, this is a 90-degree angle. So the easiest way to develop a 30, 60, 90 triangle when you can control the lengths of the legs is if you call the little leg a 1, and then the hypotenuse would be double that, and then the medium leg is whatever the little leg is, so 1 times the square root of 3. Now, just as a little catch here, because of the direction in the coordinate plane, I'm also going to throw a negative in front of that. I know that's not really appropriate to call a leg of a triangle negative, but just go with it. Alright, so that would be a fine setup. What I want you to do now is tell me the ratio for the sine of this angle right here. So sine, you can either think of it as old school opposite over hypotenuse, or you can think of it as y over r. They're really the same thing. So y over r would be negative square root of 3 over 2. We'll come back to this idea about calling the unit circle's radius a 1 in a moment. I'll show you what that looks like next. Alright, so here 210 degrees. So if I think about how big this reference angle is right here, this is 180, this is 210. So that's a distance of 30 degrees. So we have another 30, 60, 90. My favorite. Not really, I hate it. Alright, so then the little leg, let's call it a 1, but since it is moving downwards, let's call it a negative 1. The hypotenuse is a 2. The hypotenuse, the r, is never negative, so just don't worry about that. And then this value here is 1 times the square root of 3, but it is negative, so negative square root of 3. So using my old cosecant formula, or my new cosecant formula, which is r over y, that gives me 2 over y negative 1, which is negative 2. Fun, right? Totally. The cosine of negative 315, doesn't matter how you got there, the point is that your reference angle right here is a 45-degree angle. So we now have a 45, 45, 90, which means the legs are 1 and 1, and the hypotenuse is 1 times the square root of 2. So the cosine, using my new formula or the old one, it doesn't matter, x over r, or you can say adjacent over hypotenuse, it is 1 over the square root of 2, which we know we're going to have to rationalize. So my final answer, square root of 2 over 2. Whew! Alright, so back here on the idea of what a unit circle is. A unit circle is a very special circle where the radius is a 1, a length of 1. So if you accept that all the radii are 1, if I go back to these examples here, I should have done this all in the same color, this was silly of me. So like right here on this guy, if I wanted this radius to be a 1, what you do is you just come here and you cut all these by 2. Look what happens. This becomes a 1/2, this becomes a negative 3 over 2, and this becomes a 1. So why is that so important? Because if you let the radius be a 1, all of a sudden your x value and your y value become two very important trig functions. Your x value becomes the cosine, and the y value becomes the sine. But that only occurs on the unit circle. So if you want to use that relationship, you have to make sure that your radii are 1. Radii are 1. So like here, we'd have to cut everything by a 2. It's not a huge deal, but it's something. And then same thing here. I'd have to, this is kind of gross though, I'd have to cut this by the square root of 2. Blech. Now, this is where it gets kind of funky. Notice 1 over square root of 2 is not the answer we got for cosine, and that's because it had to be rationalized, remember? So they will come out to the same thing, but I don't know, sometimes I think there's too much information thrown at you in the next couple days where you're like, overload. Just stay with me, okay? This is the important topic. If you are looking at the unit circle and you have a radius of 1, which is the unit circle, then the x value is the cosine and the y value is the sine. So that means for tangent, you would have to take the y value over the x value. That would be sine over cosine. And then the reciprocal functions, all the same reciprocal properties are true. So, during class, we might have kind of stopped here and went off and did the unit circle. There's probably a separate lesson here on our YouTube channel for developing the unit circle. But what I'd like to do now is, now that we know these formulas are kind of neat, here is the unit circle. And what you're noticing is there's, obviously we didn't fill out everything in the unit circle because you wouldn't possibly be able to. We just filled out some frequently occurring key features that show up a lot in trig. So your 30s family, your 45s family, and your 60s family, the quadrangles are important. And then all the ordered pairs associated with them are very important. So go ahead to another lesson where it's probably called developing the unit circle or something cheesy like that. And we'll talk about the best way to come up with these 16 points on the unit circle and all their features. For now, what we're going to do is we're going to pretend we already have it all memorized, and we're going to use the unit circle to actually come up with some understandings of stuff. So like here, what's the cosine of 7 pi over 6? Well, if you have the unit circle and you don't have my face in the middle of it, let's get that out of there. You find 7 pi over 6, which is right here. So they took the liberty of already doing all this triangle work. Now if I want the cosine, remember cosine is the x value and sine is the y value. Boy, there we go. You know, maybe it wasn't a good idea to record a lesson Friday night. I'm tired. Alright, so cosine is the x value, and I can tell from the unit circle it is simply a negative square root of 3 over 2. So wouldn't it be awesome if you like had this all memorized? Yeah. And in calculus, you're going to have to really reference this quite a bit, so you're going to have to kind of accidentally memorize it, if not on purpose. Secant of negative 3 pi over 4. Now this is kind of a drawback because on this particular one, they don't show you negative angles. You have to kind of think real hard. So 3 pi over 4 is, you know, positive directions going positive 135. So negative 3 pi over 4 would be going this direction. We'd land at negative right here. So it's the same thing as 5 pi over 4. So the secant is the reciprocal of cosine. So if I take my cosine value, which you can take this simplified version if you'd like, which is negative square root of 2 over 2. Whoops, but I want the reciprocal of it. So I want negative 2 over square root of 2, and then I'd have to re-rationalize it. This is kind of dumb, isn't it? Because if I would have done this myself, I wouldn't have to do this time. Negative 2 square root of 2 over 2, and then the 2's cancel, and then you get negative square root of 2. Now, remember when we found that square root of 2 over 2 fun earlier? It started off as like 1 over the square root of 2. So if you had that original version of the ratio and you just flipped it, then you wouldn't have had to re-rationalize, but whatever. Alright, tangent of pi over 2. Remember this is pi over 2 up here. And tangent is, using my new formula, it's y over x. So the y value is a 1, the x is a 0, which means the tangent at pi over 2 is undefined. Which happens. Alright. The rest of the examples are kind of more of that. So I think I'm just going to stop the lesson here, guys. I'm tired, but we're about to develop the unit circle. We'll see if I can muster up enough energy to make my new lesson.